everyone. My name is Aparna Dhepe. I am from Physics Department. Our today's topic is Young's modulus of material of wire using flat spiral spring. That is one practical we perform at our lab where we find out the Young's modulus of wire. Before going to actual practical, let's discuss about few terms. First one is elasticity. We all know that when we apply force on certain materials, they deform, and there are few more materials when we remove that force, they again gain their original position, their original dimension. So those materials which shows this property of regaining their original shape or dimension again after removal of deforming force, those materials are called as elastic material, and this property is called as elasticity. But it is not possible that the materials will show this property for a long time. There is one particular limit up to which this material can show this property. Within that limit, stress is directly proportional to strain, and beyond that stress doesn't remain proportional with the strain. So that limit is called as the elastic limit, and there are few terms related with the elastic limits like Young's modulus, bulk modulus, modulus of rigidity, among which we will learn about Young's modulus. We are going to perform a practical of Young's modulus, and the Young's modulus, this term is a mechanical property of material where we find out its how much force it can withstand along with its elongation with respect to length. This is the Young's modulus actually. So here are some apparatus which we are using for practical. So this is our flat spiral spring. There is a spring, you can see. Another one, there are few weights. Each weight is of 50 gram. It is micrometer screw gauge. We are using this micrometer screw gauge for finding out the radius of this wire, material of wire. There is one more apparatus called vernier caliper. We are using this vernier caliper to find out the radius of the spring. Here is a stopwatch. So to perform this practical, what we are going to do, first with the help of vernier caliper and micrometer screw gauge, we will find out the radius of this material of wire. For that, we will put this micrometer screw gauge like this, and with all those criteria which we perform for finding out the radius, we will find out the radius of this wire. Again, using this vernier caliper, we will find out the inner radius of this spring. So that for inner radius, we will put the vernier caliper in such a way, and we will find out the radius. Then those are small r and capital R. When we will see the next part, then we will go for that. Again, we are going to measure some timings for few oscillations, like as I said earlier, each weight is of 50 gram here. This is a 50 gram weight. For first reading, I will put this 50 gram weight and give a certain oscillations to this spring. And for particular oscillation, like if I start my stopwatch and for 20 oscillation, I will count down the timing for that, like 1, 2, 3, 4, 20 oscillations. Then we will timing for 20 oscillations. Likewise, we will increase the weight 100 gram. Again for 20 oscillations, we will find out the timing. There will be set of mass like 50 gram, 100 gram, 150 gram, and again there will be a timing for those oscillations. So this is the actual performance which we do for this practical. So for the next part, we will go to the next slide. Okay, here is the actual part how we perform Young's modulus. Young's modulus of material of wire using flat spiral spring. There is one already done practical by one of our students. So you can see here is the aim of the practical, to find Young's modulus of material of wire using flat spiral spring. These are the apparatus which we discussed. This is a diagram, and here is the main formula. I will read out for you. Y is equal to 16 pi square n capital R cube divided by small r raised to 4 bracket this term capital M plus term ms by 3, and here is a capital T square. Let us see what these terms indicates. Here is another formula which we use to find out Young's modulus by graph. So let us see what these terms indicate. Capital N here indicates number of turns of spring. Small r is the radius of wire, which we find out using micrometer screw gauge. Capital R is the radius of spring, which we used by using which we measured by using vernier caliper. Capital M is a mass attached to the spring, likewise I said 50 gram, 150 gram, those individual masses, those are capital M. Ms is a mass of spring. The spring here, this mass is actually calculated one, it is 150 gram, and capital T is the time period for vertical oscillations. So here is another one. These are few observations. As we know, least count of vernier caliper, it is mentioned here 0.01 centimeter. Least count of micrometer screw gauge 0.001 centimeter. Here is one table. This table shows a radius of wire using micrometer screw gauge, small r. This is the value of small r. Again, this table shows radius of spring using vernier caliper. This is the value of capital R. When we add this small r and capital R, we come to the conclusion of capital R again. It is actually this is a R prime, and when we add this R prime to R, we find out or we get capital R. It is whatever value that student got for him. Then there is a mass of spring 150 gram, number of turns 58, and here is the actual practical which he performed. Here you can see when he added a mass of 150 gram, he find out the timing of 10 oscillations. He took 3 sets, T1, T2, T3, and he took a mean of that. Then there is a time period for, as we are using 10 oscillations, he divided small t by 10. If we are using it for 20 oscillations, we will divide this small t by 20. Then there is again another table, another column T square. Then there is a last column where it is m plus ms by 3 and this T squares division. You can see here. And the last one he got is a mean of all that. If you pay attention in the previous slide, here is a formula where we are needing this term m plus ms by 3 by T square. So this table is giving us the mean of that term which we got here. So the next part is the calculation part, where he put that value, he used here all the terms like pi, capital N, small r, capital R, all those values are written here, and by using all this value he calculated Young's modulus. You can see the unit here used is a dyne per centimeter square. This is a CGS unit, as we are using all the terms in the term of CGS 1. So the unit is dyne per centimeter square here, and you can see it is approximately right for the practical. This value is approximately right. If you want to convert this unit into SI unit, you can use the relation between dyne and Newton, and the SI unit will consider as Newton per meter square. Here is one part where we have find out Young's modulus by calculation. To find out Young's modulus by graph, here what he has done. There is a column called m plus ms by 3 and T square. Here are 2 columns. By using computer, we have generated this graph. Using computer again, we are using this slope. You can see here the coefficient of x is a slope here. So we are using directly this slope value in our formula which we have here. You can see All these terms we find out by micrometer, screw gauge, vernier caliper, but this term here the slope we use computer for that, and when we put that value of slope here, we will come to know the Young's modulus by graph. See, you can compare these two values. Obviously there are a few errors, but it is considerable as you are doing practical, but this is the right method to do that. That is again unit is dyne per centimeter square. So hence way he has completed Young's modulus of material of Y by calculation and by graph. So hence we studied here how to find out Young's modulus. There is a small question for you all. Let me know in comment section what is which Young's modulus, or sorry, which of the material have more elasticity. There are two materials, rubber and stainless steel. Tell me which of them have maximum elasticity. Thank you.